Hi all again. So in this video, we show how to compute the gradient of the flow map on three-dimensional velocity datasets. So the theory behind the computation of the flow map in 3D is essentially the same as the one that we had in 2D. So I invite you to check out the videos from the 2D computation. As I said, the theory is exactly the same. So the idea behind the gradient flow map is, suppose you have a given trajectory, this time in 3D, then you can initially attach a unit material vector C0. And this unit material vector C0 evolves along this trajectory according to this quantity here. So you simply need to take the gradient of the flow map and left and right multiply the initial perturbation C0. And then you have the evolution of this vector at arbitrary times along this trajectory. So the computation here is so the first three steps are essentially the same as in the previous videos on the computation of the velocity field or on the computation of the of an individual trajectory. The last step simply then includes computing numerically the gradient of the flow map. So the first steps here are essentially the same. I will not go through them hence. To compute the gradient of the flow map in 3D, it's a bit more involved than in 2D. If you can recall in 2D, of course, the gradient of the flow map in 2D was a 2x2 matrix. So we only had these four components up here. Now in 3D, of course, you also need to take derivative with respect to the z direction. And the trajectory is no longer defined, no longer has x and y components, but it also has a z component. To stick with the notation in the book, I denote the x component here as x1, the y component as x2, and the z component of a trajectory as x3. So this is basically the scheme that you need to have, and you need to keep in mind when you compute the gradient of the flow map in 3D. The initial quantity that you have here is this delta x and delta y and delta z. Now, what these quantities are is essentially I need to compute numerical derivatives, and hence I have these auxiliary grid basically. So I compute the gradient of flow using the auxiliary grid. The same thing that we did in 2D, now simply in 3D. So hence we need to compute these. We need to define this auxiliary grid spacing. And the auxiliary grid spacing actually is defined. So the auxiliary grid spacing is defined here exactly. So that's the auxiliary grid spacing. Of course, I need to have an initial time, a final time, and a time step, which you can make even smaller. Then you need to have the time array. Again, if you want to compute the gradient flow in the backward time direction, then you need to make sure that Tn is smaller than T0 and that dt is actually negative. So you can make sure this by just writing this so that you no longer have to care about the sign of dt. Here we define our auxiliary grid. You can actually make these terms actually even smaller if you want. Then this is the point where we want to evaluate the gradient of the flow map. So we want to evaluate the gradient flow map at this initial point here over this final time interval. And for that, we simply first actually need to import this function gradient of flow map, which again you can find in the subfunctions folder under utils. So it's here. And what arguments does this function take? Well, of course, it needs to take the time interval of which you want to compute the gradient of the flow map, the initial position, the x, y, z measured of the velocity data, the interpolance of the velocity components, whether it is a periodic or non-periodic, whether it has periodic or non-periodic boundary conditions, whether it is steady or unsteady, and of course, a list specifying the auxiliary grid, where this first component here simply would be delta x, that you can write as delta x, delta y, delta z, basically. So delta x, delta y, delta z. And what you get then as an output is basically the gradient of the flow map defined over this. Oh yeah, actually I need to run this, of course, as well. So let me run all the scripts so that I import the data. And so what this gradient of the flow map function returns is of course, it returns the gradient of the flow map at each point along this time array. Now, generally, you're just interested in gradient of the flow map from T0 to Tn. And that's why you simply just extract this last component. Because what this returns, so what this gradient flow map function returns is it returns such a type of an array where nt is simply equal to the number of time steps here specified by this time function, 3 times 3 because of course a 3 times 3 gradient tensor, and 1 because we're just computing gradient flow map for one individual initial condition. So you can see that the array that this function here returns has a shape of 1001, 3, 3, and 1. You can fairly simply verify that this 1001 is simply because the array of the time is also 1001. However, one is generally not interested in the gradient flow map over all time steps within this time interval, but just from T0 to Tn. So if we just want to have the gradient flow map from T0 to Tn, then of course we simply need to extract this. So we need to run this command. And this implies that actually grade f map T0 Tn is yes, of course, I'm missing this Tn is a 3 times 3 matrix. And if you want to take a look at how this matrix looks like, then it has the following form. That's pretty much it for the computation of the gradient flow map. It's very simple, and it's pretty much as in the 2D case, simply that the auxiliary grid here has, of course, one additional component for the z dimension, and the gradient of the flow map is no longer a 2 times 2 matrix, but it's a 3 times 3 matrix. With that, I thank you for your attention, and I look forward to the next video on the computation of the Cauchy-Green strain tensor.